Hi everyone, welcome back to our channel. Today we are going to discuss about the series connection of coupled coils. So what is the meaning of series connection? In a series connection, you can understand that current is constant in the coupled coils. So the meaning of coupled means these coils are connected together. If the two coils are connected together, then they are called as a coupled coils. Okay. So here you have two types of series connection. One is series additive, and next one is series subtractive. So what is this additive and subtractive? We will try to understand with the help of a diagram. Okay. So here I am considering one inductive coil. This is an inductive coil, and this is one more inductive coil. So let us try to understand. I am applying a voltage of V1 across this coil, and I'm labeling this inductor as L1 and I'm labeling this inductor as L2. So a current of I ampere flows will directly, and you can see this current is constant. And whenever the, as per the Faraday's laws of electromagnetic induction, as soon as the current flows in inductive coil will generate a voltage. I'm labeling that voltage as VL1, and the voltage generated across the inductor 2 I'm labeling with an name VL2, with the terminals of positive and negative. Okay, so this is positive and negative terminals. So but there exists an, so here we have an dot which indicates the direction of induced EMF. So here the dots are there at the starting of the coil, and the mutual inductance between these two coils is M12. Okay, so this is the mutual inductance. So generally how we are going to write down is, so now I'm writing the total voltage induced. Okay, so this is a positive terminal, this is negative terminal, and the current is flowing. So whenever the current is leaving, the leaving terminal of the voltage is positive. So I'm going to write it as plus V. So current is entering at positive terminal, leaving at negative terminal. The leaving terminal is minus. This is minus VL1. So current is entering at positive terminal, leaving at negative terminal. This is minus VL2, so that equal to 0. Okay, so now that's what we are analyzing now. So we successfully applied Kirchhoff's voltage law, and when trying to analyze the KVL equation, so from this we can write down V is equal to VL1 plus VL2. So this is the KVL equation what we have been obtained. Now I will write to I would like to write down the voltage across the inductor 1, which is due to self-inductance as well as mutual inductance. For VL1, I'm going to write down the voltage. So VL1 is nothing but where we call it as so KVL can be written as voltage sources. This is called voltage sources is equal to voltage drops, or we can write down it as, generally we will write down voltage source minus voltage drop. Now we'll write down as voltage source is equal to voltage drops, both are same. So voltage source is how much? VL1. The voltage across the inductor 1 is VL1. It creates a drop which is nothing but carrying a current of L1 inductance with a current of d I1 divided by dt. So this is self inductance, but there is a mutual inductance between coil 1 and coil 2. So this flux which links 1 with 2. So this coil I can claim it as phi 12. So the flux which travel from coil 1 and it links coil 2, therefore this flux is called as phi 12. What is the meaning of this phi 12 means and this is the meaning of phi 12, and there is some flux which travels from second coil to first coil. So this is the flux which travels from second coil to first coil, where we are going to call this as flux phi 2 links coil 1 with a value of phi 1. Okay, so we can call this as the flux phi 2 linking phi 1. This is called as phi 2 1. So therefore the self inductance is L into di1 by dt plus the mutual inductance between 1 and 2. What is the value of mutual inductance? M12 di1, or this I am going to call it as di1 or di2. So here there is no 1, directly I can write it as diy because current is constant. So this is how I have been written. Therefore VL1 I can write down it as by taking di by dt common in this equation. Di by dt is equal to L1 plus M12. Similarly, I would like to write down the voltage across the inductor 2. This where VL2 is called as the voltage source applied. The drop created is so here the inductance value is L2. So L2 into d I1 only have to write down. So all we are writing it as di by dt as this current, and it has an mutual flux linking from first coil to second coil. So this is the flux linking coil 1 to coil 2. That's what we are writing it as the mutual flux into di by dt. Okay, so I will make you things very clear, no need to understand. So VL2 is equal to take di by dt as common. So di by dt if you take common, which is L2 plus. So this you can write down it as M12, and you can write down M12. So overallly this M12 is also mutual flux. I will assume it as M. So therefore I can write down this as, so total V is equal to, as per this equation, V is equal to VL1 plus VL2. Therefore V is equal to, so this we can, so you can take di by dt as common here. So we can write down di by dt of L1 plus M12, we can write it as mutual inductance Sm, and plus di by dt of, what is the inductance here due to self and mutual is M2 plus L2 plus M12. So here I can write down this directly by removing the di by dt term. I can write down this as a L1 plus M plus L2 plus M. So the total we can write down it as di by dt di by dt of this value. So therefore generally the voltage across the inductance I can write down it as so L into di by dt, where this I am going to call it as equivalent inductance. Comparing these two values, L equivalent I can write down it as L1 plus L2 plus M, I can write down this as 2M. This is very important. This is the total inductance due to series connection of coils. So in order to remove the confusion, directly we will write down the inductance. This is inductor L1. This is inductor L2. So whenever the current, so here the voltage induced or indicated with the help of a dot. Whenever the current I is flowing here, how to write down the equivalent inductance is, self inductance is L1 and the mutual inductance is M12. We have to write down, how to write down is very simple. Okay, so you can see here also the current is entering the coil, here also the current is entering the coil, and you can see here the current is entering towards the dot. So it is entering towards the dot, then you have to write down plus M. So therefore here I can write down the self inductance as L1, and you can see here to these dots the current is entering, therefore I can write down as plus M. This is the inductance of first coil. How to write down the inductance of the second coil? What is the self-inductance is L2. So here the current is entering, and here also the current is entering the dot. Therefore, the mutual inductance will be plus M. So we will get L1 plus M and L2 plus M. Therefore, when you add L equivalent, which is nothing but L1 plus M plus L2 plus M, where this is called L1 plus L2 plus 2M. So this is all we had done the derivation, but a shortcut I'm saying how to solve it. So this is how we find out where this kind of is called as series connection of coupled coils. Here the flux of the both coil will add each other. So in series additive, the flux of both coils will assist each other, or they will help each other. This is called, so here in series subtractive, the flux of both coil will mutually oppose each other. They mutually oppose each other. So this like addition of flux phi 1 plus phi 2. Here it is phi 1 minus phi 2, which is called the opposition of flux will occur, which is called series subtractive. This is called addition of flux. So this is called series additive, and this is called series subtractive of fluxes. So that's how we understood. So you can see here. So this the current is entering the dot. Here also the current is entering. I can call it as series additive. How to write down series subtractive? Now we will look it here. Okay, so similarly I can draw one more connection for series connection. So this is an inductor 1 and this is an inductor 2. So let's try to draw with another color where you will get a clarity if you have any doubt. So this is an this is inductor 1, this is inductor 2, and here you can see here. So to this coil the induced EMF is at entering. To this coil, this is the dot is, I mean the induced EMF polarities are indicated like this. So now I have to connect them in series. Okay, so now the output of the coil have been connected to the input, and this is called the resultant terminal. So here we are going to apply a voltage of V volts. Therefore, whenever the current is entering, it induces an EMF which is called VL1. So this also will induce an EMF which is called VL2. Okay, so here two fluxes are there. So the mutual flux between these two coils, I'm going to call it as M12 here. So the same we want to apply for both the coils. So initially let us try to apply Kirchhoff's voltage law. So this is positive terminal, negative terminal. So now I can say that these two are in series subtractive, the fluxes will oppose each other. So this connection is called series subtractive. Fluxes will oppose each other. So why they will oppose them means here the current is entering the dot, but here this current will flow like this, and the flux, I mean the current is at leaving the dot. So here it is entering the dot, and here the dot is there whenever the current is leaving. So due to this I can call this connection as series subtractive. But in this case current is there at entering of the dots, but here the for one coil current is entering the dot, for another coil current is leaving the dot. So whenever the current is leaving, it is there leaving. Therefore this I can call as a series connection only, but subtractive, where the fluxes will oppose each other. So when you apply the KVL, the current is flowing, therefore this voltage I can write down it as plus V. and whenever the current is leaving, the leaving polarity is minus VL1. So the current flows like this and flows across this inductor, and whenever the current is leaving, the leaving polarity is minus, which is minus VL2 is equal to 0. The resultant voltage I can write down V is equal to VL1 plus VL2 is the resultant KVL. Okay. So now we want to write down what is the value of VL1, the voltage induced across the inductor 1, which is called voltage source, and we have to write down the drop. So the self inductance, the voltage across the inductor is V is equal to L di by dt. Okay, and mutual inductance is reverse. Okay, so assume this current as I. There's no need to bother two currents. Why? Because in a series connection only one current is there. Therefore VL1 is nothing but what is the inductance value? L1 into di by dt. Okay, and we can see here, to this coil the current is entering this dot. To this coil the current is at leaving the dot, therefore the mutual inductance will be of minus polarity. You have to write down. So with respect to drops I am writing, so this is nothing but minus m into di by dt is the voltage across the coil 1. Similarly, let's try to write down the voltage across coil 2 is equal to, where VL2 is called voltage source and this term is called voltage drops. Okay, so VL2 we can write down it as, so what is the voltage across the inductor? The formula is LdI by dt. What is the inductance value here? L2. Since the current is same, I am writing it as di by dt. So here you can write down this also as M12, but overall we'll assume this mutual inductance as only M. So L2 into di by d2, and here also the same, the mutual self inductance is L2 di by d2, and here you can see here, so the mutual inductance how to write down is, here to this coil the current is entering the dot, to this coil the current is there at leaving the dot. I can write down minus M12 di by dt. So now use first equation as well as second equation and apply in the original equation. Therefore, V is equal to VL1. What is the value of VL1? So here I am taking di by dt as common. So I can write down di by dt, which is L1 minus M, plus VL2. What is the value of VL2? Take di by dt as an common term. Di by dt of L2 minus M. So here what I can take common? So I can take di by dt as an common. V is equal to di by dt of L1 minus M plus L2 minus M. Therefore V is equal to di by dt. To this I can write down L1 plus L2 minus M I can write down it as minus 2M. So this is equal to standard equation. V is equal to L dA by dt, where this we are going to call it as L equivalent. So the value of L equivalent is equal to L1 plus L2 minus 2M is the inductance value whenever the coils are connected in series subtractive. Okay, so series subtractive, you can draw this series subtractive in as shown here. This is one inductor and this is another inductor. Okay, so here to this coil the current is entering, the dot is available at this point. To this current, this is available at the leaving. Okay, current is entering at this point and current is leaving at this point, the dot is there at leaving, so I can call this as series subtractive. Okay, in a series connection. Therefore two types of connections are possible in series connection. One is called series additive. Series additive means current should be there only at entering, that we call it as series additive. Therefore L equivalent is L1 plus L2 plus 2m. It's an addition of self and mutual inductance. In series subtractive, current will be there. I mean, current enters one dot and current leaves another dot, which is called series subtractive. Therefore, the L equivalent is L1 plus L2 minus 2m. Let us try to see different possible combinations. Then you can understand the things very better. So I have two inductors. This is inductor 1, this is inductor 2. Okay, so this is one combination. So next one, this is inductor 1 and this is inductor 2. So L1 L2 L1 L2. So now here I am putting the dots to make the things very clear. So dot indicates the polarity of induced EMF, which is given by the manufacturer. So here these dots are there at entering of the coil, here the dots are there at leaving of the coil. So it is apply some voltage. As soon as you apply the voltage, the current flows into the coil. So here dot is there, the current is entering the coil. Here also the current is there at entering of the coil. Whenever the current is there at both entering, therefore L equivalent as per the derivation is L1 plus M. Next one, here L2 plus M. The resultant is L equivalent is equal to L1 plus L2 plus 2M. And similarly here, in this coil also, if you apply the voltage, the current flows in L1 plus L2, but here the dot is there whenever the current is leaving. Here the dot is there whenever the current is leaving. Whenever the dots are there at leaving, I can write down as, so L equivalent of this coil is L1. So currents are there at leaving, so we can directly write down it as plus M. So here also the amount of inductance is plus L2 current. I mean, here the mutual inductance is at leaving. Here the mutual inductance is at entering. If it is there, the currents are entering at both dots entering, it is positive. If the currents are there at both leaving of the dots, then it is also positive. Okay, so here this is L1 plus M, this is also L2 plus M. So this is nothing but L1 plus L2 plus 2M, where I can say that these two configurations are series additive configurations. Coming to the three possible combinations are series subtractive configurations. I mean, to one coil, current should enter the dot, to the another coil, current should leave the dot. Let us try to see that configurations also. This is inductor 1, this is inductor 2, L1 and L2. So now I am applying some voltage, and already in this coil the current is entering like this. The dot is there at entering, and here the dot is there at leaving. Okay, the here you can see the current is entering the dot. Here to the coil 2, the current is leaving the dot. Therefore, when you write down the individual inductance, so this inductance is called mutual inductance. When you write down inductance of the first coil, this one is L1, one is at entering, one is at leaving. This is nothing but L1 minus M. So when you write down the inductance of only second coil, L2, and the mutual inductance is minus. Why? Because one is entering the coil, one is leaving, one is entering the dot, one is leaving the dot. So when you write down the resultant, L equivalent, first coil value is how much? L1 minus M. What is the second coil inductance? L2 minus M. This I can write down L1 plus L2 plus minus M. Therefore, these type of configurations are called series subtractive type of configurations. Similarly, one more configuration of same design you can understand. This is inductor 1 and this is also inductor L1, L2. So here the dots are given at this point at leaving and entering. Okay, so I apply some voltage V, automatically current flows here. Here you can see here the current is leaving the dot. For coil 2, the current is entering the dot. So you can see this current is leaving coil 1. I mean, it is leaving coil 1 dot. Here it is entering coil 2. So one is leaving, one is entering. Automatically when you write down self inductance of each coil, this is one is self is L1, mutual is one is at leaving, one is at entering, this is minus M. So when you write down for individual coil 2, One is at entering, one is at leaving. I can write down this as minus m, but self-inductance is L2. If you write down the overall inductance, L equivalent is L1 plus L2 minus 2m. Just add both the values. So these are the four possible configurations where we call it as series additive and series subtractive. In series additive, the flux get aided itself. Here in series subtractive, the flux get subtractive in nature. Okay, so there I can write down L equivalent in this case is L1 plus L2 plus 2m, where I can say current can enter both the coil. I mean current enter both the dots. Current can leave both the dots, but here current is entering one dot, current is leaving another dot, current is leaving one dot, current is entering another dot. In this case, this is called series subtractive. Amount of inductance L equivalent is equal to L1 plus L2 minus M. Hope the concept is very clear. When you come to the original derivation, this is what the basic derivation behind this and how to analyze. This type of configurations are called series subtractive and series additive. This is all about series connection of coupled coils. We'll meet in the next session. If you feel the content is useful to you, just like the video, share with your friends. If you have any doubts, let me know in comment section. And if you're watching the channel for the first time, subscribe to this channel. This is a free channel for the development and betterment of students and faculty. Yours obediently, Ram. Meet you in the next video.